Today, he is among us and going to speak on central extensions. Professor Dipendra Prasad, over to you.
All right. Thank you, Manoj. Thank you, Anupam, for starting this wonderful series on group theory. I certainly hope many mathematicians in the country will come together on this platform. So my lecture is, as I already wrote in my abstract, it is partly an exposition and partly uh, related to some work I have been trying to do with Sumana Hatui. She came to Tata Institute as a visitor. I have the feeling I have already been in IIT for 2 years, so it must be more than 2 years ago. But this work has not gone too far, so I feel a little bad about it. But in any case, it's an occasion to review some of the material and also to review what we wanted to do. Okay, so central extensions is a topic in group theory of basic importance. I hope it's visible. Manoj, is it okay?
Yes, for me, this is fine.
Little bigger is possible, perhaps.
I think this might be too big. Earlier was better, I felt.
Earlier was better? Okay, yeah. All right, Vijay. Okay, so fine, good. All right, so I am beginning with the definition of a central extension. Let G be a group, A an abelian group. A group E is called a central extension of G by A if there is a short exact sequence of groups in which A is in the kernel of the mapping from E to G. So this is often called the covering map, whose kernel is a central subgroup in the group E. And somehow the subject of central extension tries to understand what are the possible central extensions of any group G. In this talk, eventually I want to deal with finite groups, but the subject is not necessarily restricted to finite groups. The study of central extensions goes back to Schur, for whom one of the motivations for studying central extensions was projective representations of a group, which we will come to. In particular, he studied projective representations of the symmetric group and fully classified all central extensions of the symmetric groups. Okay, recall that a representation of a group G simply means a homomorphism of groups pi from G to GL and C, a homomorphism of groups in which the target group is GL and C, which is automorphism of a finite dimensional vector space. It could also be infinite dimensional, but at the moment I have just written GL and C for finite dimensional. So this is what is called a representation of a group, whereas a projective representation of a group is a homomorphism of groups in which you replace this GLN by PGLN. So it is a very analogous definition. However, much can change between GLN and PGLN. So we will come to some examples later on, but just to emphasize that linear representations with values in GL and C versus projective representations with values in PGLN, this can be very, very different world.
So there is a question since Parul Gupta raised her hand. Would you like to take the question, sir?
I would like to once in a while maybe pause, but all right, Parul. Yeah. Yes, Parul.
Sorry, there was no question. I was just trying to manage my screen and change the.
Good to hear from you. And as I said, I'm happy to take questions. Maybe every now and then I will make a pause, and then it may be an occasion to take questions.
Yeah.
Right. Good.
Sorry.
Yeah.
Sorry.
No issues. All right. Good to have you in the audience, Parul. Okay.
Thank
So this was a projective representation. So right. So this is where I was. If pi is an irreducible representation of a group G, then by Schur's lemma, the central elements in the group go to scalar matrices, and which means that pi, this homomorphism, descends to give you a homomorphism from G mod Z to PGLN. So in this sense, this linear representation gives rise to a projective representation of G mod the center. Conversely, a homomorphism of groups from G to P, GL, and C gives rise to a certain central extension of G, which somehow is said to be obtained from PGLN by pullback. So PGLNC has a natural central extension. So in some ways, I define this notion here. Given a projective representation of a group G to PGLN, I define a group G tilde, which consists of pair of elements G, X in SLNC, such that pi G, which is an element in PGLNC, is PX, where P from SLN to PGLN is the natural surjective homomorphism, which is a central extension with kernel the nth roots of unity. So this mapping from SLN to PGLNC is a surjective homomorphism, and the kernel of this mapping is the nth roots of unity. So SLN upon mu n is isomorphic to PGLN, and one is defining G tilde somehow as a pullback of this covering via the mapping pi. So, you know, if I was talking on the blackboard, I would have made some commutative diagram, but at the moment, I don't think I have made that commutative diagram. So I will leave it at that. So just to say that just like linear representations, they are projective representations of a group, and given a projective representation of a group, you can construct a central extension of the group and a linear representation of the central extension. So so I did not say that this group G tilde comes equipped with a linear mapping, which is projection to the second factor, SLNC. So, you know, this G tilde is a group. It's naturally a subgroup of G cross SLN. So it has a mapping to G, and it has also a mapping to SLNC. So that gives you a representation of G tilde with values in SLNC. Okay, so this is this first slide relates projective representations to central extensions. In many ways, this is more or less equivalent point of view to understand central extensions or projective representations. Okay. All right. So I don't want to get too much into historical points of views, but just for one slide, I want to note that, Schur initiated the study of central extensions and projective representations and what is called Schur multiplicator that we will come to, but which there are topics of great interest on their own rights, but there were certain newer directions in the subject which gave new life to the subject of central extensions. And I should certainly mention two two most famous contexts in which central extensions have been used. In some ways, the topic one is nearer to my own research area, although I cannot say I know it very well. Andre Weil wrote two papers in Acta Mathematica in the mid-60s, where he constructed an infinite dimensional projective representation of the symplectic group SPN, which carries his name, the Weil representation, and constructed as a consequence twofold central extension of SPN, now called the metaplectic group. It is no exaggeration to say that this work of Weil inaugurated the use of covering groups in number theory and representation theory, in particular in the study of modular forms of half integral weight. So, theory of modular forms of half integral weight is a very classical topic, but somehow to integrate it in the usual representation theoretic point of view, this work on metaplectic group played an important role. These works of Andre Weil are mostly written for infinite dimensional representations, but it is also possible to use these works for finite groups. So typically these are infinite dimensional, but they can also be used for finite dimensional representations of finite groups also. The other big impetus to the subject of central extensions came from the work of Steinberg, who in early 60s, in fact, he has a paper in 1962, where he constructed universal central extension of SLN, or in general, what is called any Chevalier group. So he constructed universal central extension of any Chevalier group. And these groups are these days called Steinberg groups. Steinberg's results were interpreted by Moore and Matsumoto as asserting that kernel of the universal central extension, which is H2 SLN FZ, we will come to these homological and cohomological notions soon, is equal to K2F. So, K theory was being born in these works. So anyway, K2 of a field is defined here. F star cross F star tensor product modulo these relations. I guess these works of Moore and Matsumoto are about the same time, 1968. And I think Milner crystallized the idea of K2. And so this notion of K2 bears Milner's name. Okay, so this work of Steinberg, followed up by Moore, Matsumoto, and Milner, gave rise to a large subject studying central extensions of algebraic groups on one hand and K theory on the other. So in some ways, this is also, these two themes are quite connected, and it's quite impressive that Andre Weil was 1965, Steinberg is 1962, Moore and Matsumoto is 68, 69, and Milner is 1970 maybe, or 69. So all in the decade of 60s, the notion of K theory and central extensions for fields of interest to number theorists, but also general fields were studied. All right. So now I want to interpret the isomorphism classage of central extensions in some cohomological way. So isomorphism classage of central extensions of a group G by A are parameterized by second group cohomology of G with coefficients in A. So, usually when you talk about group cohomology, you have a group and a module. The group can be non-abelian. Typically, the module is supposed to be abelian. The group can also act on the module, but here we are taking A to be trivial G module. So, okay, so therefore I give as a little bit of introduction to how central extensions are parameterized by H2GA by saying that if you have a central extension as in the very first page, mapping from E to G, then you construct a section of that group theoretic mapping. This section is set theoretic. So you just take a mapping from G to E, and then define a mapping from G cross G by this prescription. Beta of G1, G2 is SG1, SG2, SG1, G2 inverse. So if this was a homomorphism, then this will become identity, and otherwise it has some properties, and so on. Okay, so there is a definition of H2GA in terms of two cocycles upon co-boundaries, and this is what is called it, though this is the definition, and the two cocycle I have not defined, but this beta G1, G2 defines a two cocycle, and equivalence classes define U equivalent extensions. So a closely related group which comes up in the study of central extensions is Schur multiplier of a group G, which is defined to be second homology of G with coefficients in Z. So this is the definition of Schur multiplier that is officially taken for this lecture, and I believe this is the definition which is taken by most people. Schur multiplier of a group is H2G with integral coefficients. Often enough, this homology group is dual to a cohomology group, especially in this context. So Q mod Z is roughly C star. So this is an injective abelian group, and therefore X1, this X is 0, because by definition X are supposed to be deviations of objects from being injective. Hence, by the universal coefficient theorem, which is stated here, H2 of G with Q mod Z is Hom H2GZ Q mod Z. So A is Q mod Z here, and I am just reading this, putting this to be 0. So I'm putting this object to be 0 because, as I said, if A is Q mod Z, then this object is 0. And then second cohomology with coefficients in Q mod Z, or this is same as coefficients in C star, is same as H2GZ Q mod Z. So, you know, this object is called the Pontryagin dual. So if we are looking at G a finite group, then this will be a finite group, a finite abelian group, and this is the dual of that abelian group, which is isomorphic to the abelian group, but not canonically. So if you are given an abelian group, then its dual is isomorphic to the abelian group. Okay, all right. So we observe that this mapping is surjective. So surjectivity, and whereas this one classifies extensions of G by A. So we can also classify, we can take A to be H2GZ. So, you know, you take the simplest possible option for A in this object, where you will be looking at Hom H2GZ to Hom H2GZ, because A is H2GZ, so there is the identity map. So there is the identity map here. So you construct an element here in H2GA, which goes to the identity map. So that will give rise to a central extension of G by H2GZ, which goes to the identity map here. In general, because this object is non-trivial, the central extension that one constructs is not unique, and there is that word which is used, Warsal central extension of G, but I will not get into much detail about that. But in any case, there is a central extension, perhaps many, of G by H2GZ, which go to identity homomorphism here. So these central extensions are called Warsal central extensions. So if H1 is trivial, so okay, so here are the two extreme cases of groups of interest to mathematicians. One is when G is its own commutator, which means that G abelian equals G equals H1GZ equals identity. So if this is the case, then this group is trivial. This group is trivial, and in that case, these two groups are isomorphic. And therefore, somehow there will be a universal covering whose kernel is H2GZ. Good. So this is, yeah. And then there is the other group where G is equal to G abelian, which means that it's an abelian group. So somehow there is a lot of differences in study of central extensions of type 1 versus central extensions of type 2. So I must say that I am more used to type 1, but in this work that I wish to report today with Sumana, it is more nearer to abelian groups. Nilpotent groups are nearer to being abelian than to these ones are called perfect groups, to being perfect. So it is the second case that we will have to think about. So maybe I will just finish up to here and then pause. So let us consider the first case where the G abelian is 1, which means that the group is its own commutator. These groups are called perfect groups. In this case, central universal coefficient theorem reduces to this statement, and then there is beautiful central extension G tilde of G by H2GZ, and it classifies all central extensions. So in some sense, this one extension does a beautiful job, and it's unique, and all beautiful things happen. In the other extreme case, G equals abelian group, and for abelian group, the second homology is second exterior power of G. In any case, we will be looking at central extensions of G by H2GZ. If it is perfect, then this extension will be called universal central extension. And if the group G is not perfect, then also we can consider central extension of G by H2GZ, but which we will once in a while call them to be Wurzel central extension. All right, so at this point, I will take a pause, and I'm happy to, I don't see any questions, or do I see? Okay, good. All right. Parul, I'm happy to take any questions from you. But no, I did not mean to say you in particular, but to anyone else. I am happy to take a pause and talk to you on any general matter, which is what I have covered in the first few slides, a little bit of history, and then what is a central extension, and the central extension, of course, in topology, you have the concept of a covering space. And if you take a topological group and its covering space, then those give rise to central extensions of the group. So somehow central extensions come in the subject of Lie groups or topological groups via fundamental group. But fundamental group usually is studied for connected topological spaces, whereas here our objects are finite groups. Somehow primary object of interest for my lecture and in general is finite group theory. Of course, finite group theory is the most difficult subject in mathematics. So that has to be kept in mind. All right, shall I go on? So, of course, any subject gets its interest by the depth and beauty of its examples. And theory of central extensions, I already told you names of Andre Weil, and then Steinberg, and Moore, Matsumoto, and Milner. Milner has one of the great books on the subject, which I have been studying for last 40 years, and still I cannot say I know it fully. But anyway, it's kind of a model of mathematics that we all have grown up with. All right, so good. Before I launch into a little bit nearer to the topic at hand, I just want to say a few commonplace central extensions. Of course, there is always the trivial central extension, which is the product of the groups. So just to say that, I mean, this extension is said to be trivial if there is a section. So if there is a mapping from G to E, group theoretic homomorphism, which when projected to G becomes identity on G, then this central extension is called trivial, in which case E becomes isomorphic to G cross A, and the mapping from E to G is the projection to the first factor. Okay, good. So this Z mod 2 by Z mod 2. So there are two extensions in this case. One of them is the trivial extension, which is always there. Somehow this interest in the subject is to understand the non-trivial extensions. And there is one non-trivial extension, Z mod 2, Z mod 4, Z mod 2. So I must say that, the way things have been set up, even this extension we will not really worry about. It is, of course, important and beautiful and non-trivial extension, but the way we have set things up, this extension will become trivial. Because what we are going to do in this lecture and in this subject is to replace this group A by a homomorphism of A to C star. So, we are not so much interested in central extensions by A, but by, so to say, C star. And so for that reason, although this extension has to be kept in mind, you have to also keep in mind that it is some kind of, so it's although non-trivial, but for our purposes, it is trivial. All right. So what is non-trivial is certainly this extension, which is favorite of all of us. It's called the Heisenberg group. So it is a group which is an extension of FQ to the power 2n by FQ. So it's an exact sequence of groups in which this is a non-abelian group, Heisenberg group. And these are abelian groups. This is a central abelian group. The simplest way to understand the Heisenberg group is the group of n plus 1 cross n plus 1 upper triangular unipotent matrices with only non-diagonal non-zero entries in the first row and the last column. So I will let you imagine it is n plus 1 by n plus 1 upper triangular unipotent matrix, in which the only non-zero entries besides the diagonal, which are 1, 1, 1, are entries on the top row and farthest most column. First row, last column. So this is a group. It's a non-abelian group, and that is called the Heisenberg group. So this example and this example are somehow different. One difference is, of course, that this is non-abelian and that is abelian, which is, I think, which makes things a little more easy. Okay, so Heisenberg groups, good. All right, so I want to say that central extensions come, So in this case, you look at SONR, which is orthogonal group defined by the quadratic form x1 square plus xn square. And if on each xi you make plus minus xi, then that gives you Z mod 2 to the power n, but then the determinant which is plus minus 1, so that will give you Z mod 2 to the power n minus 1. The special orthogonal group over reals has the well-known and famous spin cover. There is a two-fold spin cover, and you can pull back this cover to plus minus 1. So that will construct for you a two-fold cover of plus minus 1 to the power n minus 1. It's a non-abelian group of order 2 to the power n, because this is 2 to the power n minus 1 here. And there is a kernel of Z mod 2. So, so there is some statements about center, etc. And the point is that the Z mod 2 to the power n minus 1 abelian group has a somewhat non-trivial non-abelian cover. So, it's so in this case one will be saying that one is getting a projective representation. Yeah, so I will come to that. So right. So you see, spin groups has a very famous spin representation, and that can be treated as a projective representation of this abelian group Z mod 2 to the power n minus 1 of dimension roughly 2 to the power n by 2. So in the usual theory of linear groups, abelian groups are not very interesting, but in the theory of projective representation, an abelian group can have a very complicated representation. So this simple-minded abelian group has a complicated projective representation. So a similar story can be done on alternating group. By permuting coordinates, you can make an sit inside SON, and again pull back the two-fold cover of spin, and that gives you the two-fold cover, a two-fold cover of alternating group. And it can be described in some explicit and nice and beautiful way. People know generators and relations for symmetric group, and these are generators and relations for the two-fold cover Sn tilde. Okay, so here is some theorem due to perhaps Schur. Let An tilde be the two-fold cover of An, which is the restriction of the two-fold cover Sn tilde of Sn. An tilde is a non-trivial two-fold cover if and only if n is greater than or equal to 4. If n is greater than or equal to 4 up to isomorphism, An tilde is the only non-trivial two-fold cover of An, which is isomorphic to the two-fold cover of An obtained by the pullback of the spin cover. Good. Okay, so in some sense, many at least these two examples, quite striking examples of coverings were constructed by pulling back spin covering, and therefore there is a natural question which comes to one's mind. So suppose G is any finite or compact connected Lie group. Question is whether any two-fold cover of G is obtained from pullback of spin cover through a homomorphism from G to SON. So, in fact, as I was making these slides, I was thinking that I will ask Steve Spellon whether this is true or not, because I know that he has studied coverings of the compact Lie groups coming from the two-fold cover of the spin group. So I have the feeling that in this case, of course, the subject of compact connected Lie group is not terrible, and I hope he already knows the answer. I see that he is here, so I hope Steve Spellon will tell me that it is true. But of course, for finite groups, it is another story, because as I said, finite groups are way beyond much more complicated, and whether any two-fold cover of a finite group comes from spin cover is not clear. In fact, last year I was asking this question to Robert Grice, and he was not clear. He said maybe it is not true. So I also tend to feel that maybe finite groups, it is not true. But in any case, here is, so you cannot answer one question, you ask more questions. So here is a more general question. The question is whether cohomology of G with Z mod 2 coefficients is generated by what are called Stiefel-Whitney classes of orthogonal representation. And as we know that the fact that two-fold cover gives rise to an element in H2G Z mod 2, and whether that comes from second Stiefel-Whitney class. Okay, so this construction that I just talked about for orthogonal, these are compact groups and all that, can also be done for unitary groups. And the question is to ask which cohomology classes, let's say mod P coefficients, arise from Chern classes of unitary representations. So these questions to me look like analogs of what is called Hodge conjecture in algebraic geometry, which are about which cohomologies arise from Chern classes of vector bundles. They seem close. So, okay, so I will now get into finite group theory, but before that, maybe I can pause for a moment and see if anything is there. Anupam, you want to ask anything?
I'm fine right now.
Yeah, good. All right, no, wonderful. Good. All right. So these were all some generalities, which is maybe to make you think that studying of Schur, study of central extensions, which is same as studying of H2G of Z, second homology of the group with integral coefficient, or second cohomology of G with Z mod P coefficients, is a worthwhile endeavor. And now I want to talk about finite P groups. And this is where this problem that I have been thinking about with Sumana arises. So, okay, so P is a finite P group. One studies for any group, one can study its mod P cohomologies. H0 is Z mod P, H1 is homomorphisms from P to Z mod P, H2 of P Z mod P is closely related to H2P Z mod P, etc. And somehow we are interested in this object. Yeah. Okay. So I will have occasion to use this kind of Nakayama lemma, which says that if P is a finite P group and P star is the intersection of kernel of all group homomorphisms from P to Z mod P, it is the intersection, so that P mod P star is what may be called the maximal Z mod P to the power D quotient of P mod P star. These groups are called elementary abelian P groups, and we want the maximal elementary abelian P group, which is a quotient of P. And this group P star has a name, it's called the Fratini subgroup. But I don't want to bring you with names, however important or famous they might be, but it may confuse. So in any case, this P mod P star is by definition some Z mod P to the power D, and the lemma, Nakayama lemma, says that certain elements G1, Gs generate the group. So there is a typo. This should be P. Generate P if and only if their images in Z mod P to the power D generate Z mod P to the power D. Okay, so I will talk sometimes about generators, and that is what it means. Okay, so the following theorem due to Venkov brings methods in algebra to group cohomology, and here is the statement. So suppose G is a finite subgroup of the unitary group, and this gives rise to a mapping on what is called classifying spaces. I will not get into that, but anyway, the upshot is that there is a mapping from cohomology of classifying space of UN to cohomology of G. So whenever you have a mapping from one ring, one algebra to another algebra, this algebra becomes a module over this algebra. So cohomology of G Z mod P becomes a finitely generated module over this cohomology, and this cohomology is well known that it is generated by the Chern classes, so it's a polynomial algebra. So you get the cohomology of a finite group is therefore a finitely generated module over a certain polynomial ring. It is indeed a bit. So yeah, so although the group is finite and the coefficient is finite, cohomology is quite difficult. Yeah, in some ways, I should pause to let you grasp that although we have a finite group and the coefficient system is finite, therefore each one of these is finite, but altogether it's a huge object. So in any case, cohomology of G Z mod P is a vector space over Z mod P, and you can look at its dimension and you put it in the usual Poincare series or Hilbert series or whatever it is called. And the Poincare series has this form, 1 minus t to the power 2i, and then there is some integral polynomial RT. So in fact, yeah. So in this one, this also gives you an example to keep in mind what is the simplest structure of these cohomology algebras. So this elementary abelian group Z mod P to the power D, its cohomology algebra with coefficients in Z mod P is exterior algebra on generators E1, E2, ED, which are in degree 1, multiplied by polynomial algebra on generators F1, FD, which are in degree 2. So degree 1 generators and degree 2 generator. So if one was doing it in Z mod P to the power D, where D is equal to 1, then you know this will be in degree 1 and that will be in degree 2, 4, 6, and together with degree 1. So each degree will be accounted, but degree 1 and degree 2 have different roles to play. One comes from exterior algebra consideration and the other comes from symmetric algebra consideration. Okay, so the natural mapping from P to this one gives rise to an algebra homomorphism. You know, so these are cohomology theories, so they go in the other direction. So from cohomology of this to cohomology of that, it would seem more natural to study this as a module over this. So I should say I have not seen this, but the subject is a very mature subject, and I cannot imagine that people have not proved analogous theorems of this kind. So there must be, but yeah. So this is what it is. I pause for a moment. So, right. So you know, the project that I am doing with Sumana is to understand when the Schur multiplicator of a finite P group is trivial or non-trivial. And I want to first say what are the results which are known, and right. So these are the results known. If G is a finite, so all the groups, P groups are finite P groups having at least 2 generators X and Y. So these are generators in the sense that, you know, they are X1, XD, and they commute. Then the second cohomology is non-trivial. If G is a non-abelian P group such that all elements of G have order less than or equal to P, then again the cohomology is non-trivial. And in some sense, the big theorem in this subject is this theorem due to Goulart and Shafrovich. If a P group is generated by 4 or more elements, then the second cohomology is non-trivial. So in some sense, maybe this theorem alone is good enough to justify the interest in Schur multiplicator, as it is called, Schur multiplicator, and central extensions. Since this is a forum of group theorists, I don't want to get into number theorists, but of course, many people in this audience know very well that there was this famous problem in number theory that called whether the tower of class fields, whether it terminates, which means that given a number field, you can look at maximal abelian extension, which is unramified, which is finite extension, and whose Galois group is the class group. Class groups are finite groups. And then once you have reached the Hilbert class field, you can again take Hilbert class field of Hilbert class field, and so on. And the question, I do not know, maybe by Hilbert, was whether this Hilbert class field towers, do they terminate or they can keep going? And this is the famous theorem of Goulart-Shafrovich, of which indeed this group theoretic part is the key to their proof. So indeed, there is some observation about cohomology in number fields. But then this key fact from group theory is to be proven. And so not only did Goulart-Shafrovich identify the problem, but they also proved this. So this is, so indeed. So these are groups, P groups, where the Schur multiplicator is non-trivial. So you see what it says. Okay, I should have also said right at the beginning that a P group, if it has only one generator, it must be a cyclic group. And cyclic group, the Schur multiplicator is trivial. So there is not much to be said. If there are 4 or more generators, then again Goulart-Shafrovich says that it is non-trivial. So the problem is only when there are two generators or 3 generators. And the question is to find a way to understand if a group has only 2 or 3 generators, whether the Schur multiplicator is trivial or non-trivial. So that is the problem which I was trying to do with Sumana. I should say that many papers have been written on this topic. Many examples have been constructed of both trivial and non-trivial Schur multiplicator. So I give you 2 examples here where the Schur multiplicator is trivial. So here is Z mod P power N, semi-direct product with Z mod P power M. So this is the smaller group operating on the bigger group in more or less the obvious way it can. And then this so I guess I have messed it up. I should have said that the Schur multiplicator of this group is trivial. And that is a consequence of what is called Hochschild-Sayre spectral sequence. In this group, there is a normal subgroup and a cosine group, and you play with that, and it's a simple consequence of that. Right. And then there is a group of order P to the power 5, which is, so to say, Wurzel central extension of the Heisenberg group that I talked about. So Heisenberg group has order P cube, and its second homology with integral coefficient is Z mod P plus Z mod P. So therefore, it has a Wurzel extension of order P to the power 5. And Sumana has told me that this group, which is 2 generated, has Schur multiplicator 1. Okay. Good. So there are these examples. So mostly Schur multiplicator is non-trivial. There are some cases in which it is trivial. You see nilpotent groups. Nilpotent groups which are generated by two elements are also a lot of them, infinitely many, and which are generated by three are also infinitely many. And a specialist, of course, perhaps recognize those groups well. Sometimes Sumana will say that number of groups of this kind are 50 or they are 100, and it's a bit difficult to for somebody not so much trained into P group theory to understand what's going on. So, okay, so here was what I was trying to propose. Our work proposes to study Schur multiplicator by constructing central extensions directly from some very simple-minded central extensions. So even in cases of 4 or more generator where Golart-Shafrovich has given you the answer that the Schur multiplicator is non-trivial, the question is whether one can construct them in some simple way. And so ideally, we would like to say that if the Schur multiplicator is non-zero, there is this quotient P by P star Z mod P to the power D. That's a certain vector space over Z mod P. So you can just use an abelian group, and this abelian group V has a Heisenberg group-like construction. This is what one may call Wurzel central extension of V. So, you know, I said that for abelian groups, second homology is related to H2. So maybe I will go back. These slides allow me to navigate here. So the second homology of an abelian group is exterior 2, which means that any abelian group has a central extension by exterior 2. I said it's not canonical. It's not canonical, but there is one. Okay. So, right. So there is a Wurzel central extension. Of course, just like the Heisenberg group, this group is quite simple-minded to construct. You will take a pair consisting of lambda comma v, and you will make a law of addition. Lambda 1 v1 plus lambda 2 v2 is lambda 1 plus lambda 2 plus v1 wedge v2 and v1 plus v2. So it is the usual, you know, you have seen how to add elements in the Heisenberg group, and this is, so to say, universal Heisenberg group-like construction. And the most primitive hope would be that if the Schur multiplicator of P is non-zero, so, you know, you are wanting to construct central extensions of P. This gives you a central extension of V, which is a quotient of P. You can pull it, and then it gives you a central extension of P. And this is the most primitive hope one could have. Okay, good. But better still, maybe this statement is true. Not only one, but all central extensions come from here. So there is, because of this maximal elementary abelian P quotient, these two groups are isomorphic, and this isomorphism on H2 induces a surjective map. So surjective means it constructs all. If this is 0, then of course you construct nothing. So this would be good. However, it is not true that H2P Z mod P always captures, is always captured by this. For example, it is known that the Heisenberg group H3 of order P cube has a non-trivial central extension. This we will come to. In this case, P mod P star is Z, so we are looking at P to be the Heisenberg group of order P cubed. In this case, this quotient that we are talking about is Z mod P plus Z mod P, and this has a unique non-trivial central extension, which is the Heisenberg group, which when lifted to S3 gives the trivial extension of the Heisenberg group. It is just the definition of pullback of a covering. So this most primitive hope is not so good. All right, so since I am nearing 5, I will seek some permission from the organizers. I started maybe 7-8 minutes late, so I hope I have some grace period allowed to me. Anupam, will you give me some few more extra minutes?
Yes, please go ahead.
Right, yeah, good. So, okay, so this most primitive hope was that the Schur multiplicator is coming from just the abelian quotient is not good. So the next best one would like to do is use a little bit of non-abelian groups to construct central extensions. So in some ways, any P group has, so to say, maximal elementary abelian P quotient, but then it also has what is called the descending central series and so on, and you can construct a certain quotient of this group that I have denoted here by this, the middle object, and this is a central extension. So maybe central extensions of P do not come from P mod P star, but they may come from little larger quotient, which is a bit non-abelian, P mod P2. So in some sense, what one is implying is that not only you look at abelian quotients, but you also look at quotients which are Heisenberg group-like quotients and incorporate them, so they are not too complicated. And the question is whether all the Schur non-vanishing of the Schur multiplicator, or in general the full Schur multiplicator, comes from pullback of Schur multiplicator of this group. Okay, so now I want to talk about some of those known results that I spoke to you about. Yeah, so in these three known results, I think these are some kind of elementary propositions. This one is a bit of a serious theorem. So we have no approach yet to not only not to do it, but to know whether elementary abelian P quotients are adequate. So this hope that I was having, whether this hope is valid in that case or not, we are not in a position to decide. But in any case, here are some simple-minded propositions. If G is a non-abelian P group such that all elements of G have order less than or equal to P, then the Schur multiplicator is non-trivial, and we are in one of the following two cases. G has Z mod P plus Z mod P as a quotient, but does not have Heisenberg group as a quotient, in which case the central extension of Z mod P plus Z mod P given by the Heisenberg group when pulled back to G gives rise to a non-zero element of this. So this was the primitive hope that I was talking about. So this does happen. On the other hand, if G has the Heisenberg group as a quotient, then you can take a central extension of the Heisenberg group by Z mod P, and when pulled back to G, it gives rise to a non-trivial element of the Schur multiplicator. So in some sense, this proposition justifies a little bit of thinking that abelian quotients or next to abelian quotients may be adequate to give rise to enough Schur multiplicators. So the proofs are very, very elementary. I anyway have not much time. Okay, so this is the other one. If P is a P group having two generators X and Y, and I told you what the generator means, then the second cohomology is non-trivial, basically because if the second cohomology was trivial, then it means that some mapping will lift to some Heisenberg group, but the Heisenberg group is non-abelian, and these objects are commuting. So somehow it's a simple argument. Okay. So I want to end my lecture with two further thoughts on this theme of central extensions, which are related to the problem at hand. So, we have already encountered what I might call the Heisenberg extension, lambda 2 V E V, where V is a vector space of a finite field. And this extension, is one of the first central extensions of interest. So I want to say that extensions of this kind appear in nature. So I am trying to define that. So this is defined using what is called the descending central series. So let G be any group. Define inductively the subgroups Gn plus 1 to be G bracket Gn for n greater than equal to n greater than equal to 1. And as you all very well know, when you define nilpotent groups, etc., these things are done, that there is a central extension of G by Gn by Gn by Gn plus 1. So this can be done for any group G. But okay, so then the little bit more, which you may or may not always be doing, is that there are these abelian groups Gn upon Gn plus 1. So you have a group G which comes equipped with a filtration, and you can look at associated graded of that filtered object, and that becomes a Lie algebra in a natural way. You just take an element in Gn upon Gn plus 1, Gm upon Gm plus 1, and you look at the Lie bracket, just the commutator, and that commutator gives rise to a Lie algebra structure on this object G. And the interest is that if G is the free group on D symbols, then each of these is a free abelian group of finite rank. And G in that case is an explicit Lie algebra called the free Lie algebra on D generators. So, okay, so this, of course, I will not tell you more, but anyway, it's a, the notion of a free group and free abelian group and so on, you know very well, and it is in the same sense that it is a free Lie algebra. It has no more relations than Lie algebra hypothesis imposes on it. Okay, so from that point of view, just like free groups and free abelian groups and polynomials, etc., have nice set of generators, free Lie algebras have nice set of generators, and one knows that its rank is given by this beautiful formula, where mu(n) is the usual Mobius function which you study in the theory of numbers. So for instance, here I have given a few examples. LD1, so it is G is free group on D symbols. So LD1 is D, LD2 is D square minus D by 2, LD3 is D cube minus D by 3, and so on. So I would like to believe that if G is the free group on D symbols, the exact sequence 2 and its mod P analog defines a versal central extension of G mod Gn. In particular, H2 G mod Gn Z has rank this. So, I said that this exact sequence is a generalization of this exact sequence. And this way one is getting certain central extensions. Right. So this fits well with some of what we said, but doesn't fit well with some of what I did not say. So if you do this for D equals 2 and N equals 2, then it gives you the first exact sequence that I talked about. For N equals 3, it gives rise to the central extension of the Heisenberg group, Z mod P by Z mod P square, which seems good, as one knows that this one, the Schur multiplicator of the Heisenberg group, is Z mod P square. So it looks good. However, at the next level, the exact sequence gives rise to a central extension of, so to say, central extension of the Heisenberg group by Z mod P cube, which seems a bit of a problem, as Sumana tells me that the Versal central extension of H3, so this is not H3, but Versal central extension of H3 by this has trivial Schur multiplicator. So I am a bit confused what's going on. All right. So maybe this is my last slide. Many people know that finite P group theory is very closely related to nilpotent Lie algebras, say over real numbers. Of course, nilpotent Lie algebras over reals, I do not know if they are classified or they are simple, but certainly they are nowhere near as difficult as finite P groups. So one would say that there is analogy, but finite P groups are infinitely more complicated than nilpotent Lie algebras. And but in any case, the questions that we are studying seem to suggest that we answer a question about nilpotent Lie algebras, whether they can have second cohomology 0. I have not thought on this, but perhaps somebody in the audience knows how to answer this question. There are famous theorems due to constant about cohomology of nilpotent Lie algebras. I should have checked with that, but I have not. I hope there are not many for which H2 is 0. Perhaps only in dimension 1. Okay, so that's all that I had to say. Thank you very much for your attention.
All right, thank you very much. Are there any questions, comments, queries?